is by Nathan Lindzey, and he's going to tell us about representation theory and relations to TCS and extremal combinatorics. So take it away.
Thanks. So thanks for sticking around for the last talk. So it's a survey talk, so hopefully this is appropriate for the last talk so we can relax a little bit. Won't have to follow too many proofs. So here's the outline. So I'm going to start off by describing a suitcase for traveling beyond the Boolean cube. And then I'm going to argue that you already have some clothes packed in this suitcase, but you don't know it. And then once I do that, I'm just going to tell a bunch of short stories about how representation pops up in places like extremal combinatorics, Boolean functions, and places you wouldn't expect in like theoretical computer science. Okay, so this suitcase that I'm talking about is association schemes. Okay, so we're going to define these. So just let Xn be a set. And I have a bunch of matrices now, and I'm going to insist that they're binary, and I want them to be indexed by the elements of my set. So as we progress, you'll see that these matrices must have more and more structure. But for now, binary matrices. Okay, so we say that it's an association scheme if we have A0 is equal to the identity matrix. If I'm inside A, then so is my transpose. Okay, so if I'm one of these A matrices and my transpose is also in there. And then I need the sum of my matrices to sum up to the all ones matrix. Or sorry, the all ones matrix, which we're denoting as Jn. Okay, so this condition 3, you can think of these AIs as being like standard basis vectors. So that's a good way to think of them. Okay, so when I sum them up, I get the all ones matrix. And then this last condition here is that it's a strong one, and I want these matrices to commute. Okay, and these PIJKs, we call these things structure constants. So these are the structure constants of the algebra generated by these AIs. Okay. So in this talk, most of these matrices that we're dealing with are going to be symmetric. Okay, so the 2 will be vacuously satisfied. And then we call it a symmetric association scheme. And these AIs that we have here, we're going to call these associates, hence the name association scheme. There had to be a reason. Okay. So yeah, the span of this, it's a fancy name, the Bose-Mesner algebra. Don't be scared by it. It's just, you know, we're just the algebra generated by these AIs. So, you know, what makes association schemes really cool is the fact that we have this nice duality. So if I satisfy all these axioms of an association scheme, then I also get for free, I get a dual basis. And this dual basis is in terms of these, the technical term is a primitive idempotent, but these things are eigenprojectors. Okay, so they're positive semi-definite matrices and they project onto eigenspaces. And I get that E0 has to be the all ones matrix normalized. So automatically, if this is one of my eigenprojectors, then I know that my AIs, they have to be regular. So these AIs, these associates, these are just regular graphs, and they're like they have a lot of nice combinatorial regularity. Okay. For this talk, yes, yeah, but in general, they don't have to be.
So, is your axiom that they just commute, or that their product is in the span of the both?
Yes, both.
Both. Okay.
Yes. Exactly. Okay, so this property 3 is important. So it's these primitive idempotents, or these eigenprojectors, they give me a resolution of the identity. And I have this interesting last condition. So these QIJKs, these are known as Krein parameters. And you can think of these as being like dual structure constants. And this product that we have now is it's entry-wise. So this is the freshman matrix product, if you will. Yeah. So, so yeah, I mean, it's quite obvious that the symmetry that's happening here. So this is a really beautiful duality property here. And I think a lot of us are comfortable with abelian groups. And you know, if I just let these AIs be permutation matrices that realize some abelian group, and then I get that these EIJs, these are just you know, matrix versions of the dual characters. And this entry-wise product that we're doing is like point-wise product that we get with the dual characters. And so, yeah, this is kind of boring if you're just doing abelian groups. So let's make things interesting. So these AIs, let's let them be normal Cayley graphs of a non-abelian group. And so by normal Cayley graphs, we mean that their generating set is a conjugacy class. So each of these AIs, think of them as being the adjacency matrix of a normal Cayley graph generated by conjugacy class I. Now, the matrix product here is just a concrete realization of a convolution. And so we know that if we, the order in which I do convolution in a group algebra doesn't matter. So we have commutativity for free. And so I'll get to that later. But anyways, these structure constants, they're actually counting something combinatorial, but these QIJs, we sort of don't know what's going on here in general. So algebraists love to study these Krein parameters. So clearly these PIJKs, they have to be like integers, positive integers. And these QIJKs, though, these could be, you know, these could be even irrational. So this is sort of an open question in algebraic combinatorics. Can you actually make sense of these Krein parameters? And they pop up in quantum computation a lot. So with some joint work with Ansis Romanis, we characterize the Krein parameters of this association scheme that comes from the symmetric group, but they're important. And so definitely worthy of study. And I want to finally note that, so I have two bases. I have a primal one and a dual one. So anytime you have two bases, you have to ask, okay, what's the change of basis matrix? So turns out that this matrix P is what we call the character table of the association scheme. And this is just a transition. This is just the transition matrix between these two bases. And you're probably wondering, why are you calling it a character table? Well, I've sort of hinted that these things, you know, there's a natural way that we can embed groups in this more general scheme. But so this, even for non-abelian groups, this character table P, so it's not quite the character table of the group. There's some row and column normalization, but that's essentially what it is. Okay. But okay, so you're probably wondering now, okay, so we have this thing called an association scheme, and the two examples you've given me, I could do this without all this extra framework. So what's the trick? So turns out that these association schemes, you can do, like, there are domains that aren't groups, and that's when things become way more interesting. And so this this title here, it's been association schemes have been called like group theory without the groups. And so we'll see some examples of what we mean by this. And I think this is this quote's attributed to Banai and Ito, who wrote one of the first textbooks on association schemes. Sorry, I got my back turned to this side. I'll try to orient myself over here. Okay, so I want to argue that we've already seen some examples of association schemes that aren't necessarily groups. So one is the Hamming scheme. Okay, so I take words of an alphabet of size m, and I take two words and I look at their Hamming distance. If their Hamming distance is I, then in the associate AI, I put a 1 in that entry. Okay. The Johnson scheme. I take two K sets. I look at the intersection. If it's K minus I, then I put a 1 in the AI entry for that pair of K sets. Okay. And these Johnson schemes, think of these in HDX, these are just the levels of the complete complex. Okay. And so we've also seen the Q Hamming scheme. So this is also known as the bilinear form scheme. And for the condition for being, this notion of distance in the Q Hamming scheme, I take two matrices and I look at their difference. And if their rank, if they differ by a rank I matrix, then I put a 1 in for the ith associate. And finally, the Q Johnson scheme, which is the Grassmann scheme. So again, I take two K-dimensional subspaces I take their intersection. If their intersection has dimension k minus I, then I put a 1 in the AI column or in the AI entry. Okay. So I think we all know that you can work within these domains without knowing anything about group representation theory, and this is historically this was the case. Like you could completely understand these things using either inclusion matrices. These are things that we would call Juntas. So these are kind of just these matrices where I have indexed by objects of size, say k, objects of size kj. Or indexed by objects of size j, and then you look at the entries, and you have if j is a sub-object of k, then you put a 1 there. Okay. So we would call these Juntas. Okay, but they didn't call that. They didn't call them such things back in the day, and also these things called orthogonal polynomials that I'm not going to get into. Okay. So there's more structure that we can put on an association scheme, and it makes it more interesting. So in particular, it's this idea of being metric. Okay, so I haven't really talked about the ordering of these associates, but you could have ordered them arbitrarily. But for being metric, this means that I have an ordering of the associates such that the first associate generates the rest. In particular, if I look at the dth associate, I can write that as a polynomial of the first associate. Okay, so think of this like, think of A1 as being like the hypercube. If I wanted to get something at distance d in the hypercube, I'd take a walk of length d. And then I'll have some other walks that aren't short as paths, and so I have to subtract off by some lower degree polynomial to get rid of those. But the hypercube satisfies this. So if we look at the Hamming cube and make A1 be the hypercube, then we've shown that it's metric. So on the dual side, we say that an association scheme is cometric if I can order these eigenprojectors now in a similar fashion, so E1 through EM, such that there's a degree, so that I can write the dth projector as a polynomial of degree d. Where here my multiplication is again the freshman multiplication. Okay, and so I argue that this is all old news to us. This is just these are the Fourier levels on the hypercube. Okay, so I can write a pure degree function as a polynomial of degree d in the dictators, no sweat. Okay, and so when the association scheme people say cometric, we're just thinking of like Fourier levels, and so we have this nice way of ordering the levels. Where we start with things of low complexity, and then things that are higher degree have high complexity. Okay, so this hypercube, this Hamming scheme where we have a 2-letter alphabet, this is a metric and a cometric association scheme. Okay, so here we are on Earth over here, and I think part of this program is to find Earth-like planets and other places of math. So I argue that these metric and cometric association schemes, these are going to be the closest planets to being Earth-like. And many of these association schemes that we've already seen are in fact metric and cometric. So maybe this is this could be, I don't know, the Johnson scheme. That's the bilinear form scheme. That's the Grassmann scheme. But there's these other planets out here that exist that I haven't really seen anybody take a peek at in the TCS literature. And they come from things in finite geometry. And so I won't get into it, but there's lots of other association schemes that are metric and cometric. And maybe this is the right abstraction for talking about global hypercontractivity, and maybe these graphs like the short code Johnson and the Grassmann graph. So they're analogs of these for other association schemes. And maybe these also have this property where like there's only a handful of bad small set expanders. So I'll just throw that out there. It might not be the case, but it would be very strange if something were true for these suspects, but not the whole family of distance regular graphs. So, and it's also a pretty rare property. So it's, I think that most people think that there's finitely many of these metric and cometric association schemes of unbounded diameter. So there's lots of little sporadic examples that you can find, but there seems to be, like, maybe there's only finitely many of these Earth-like planets. So, but there's lots of other planets out there. In particular, a lot of them come from the Symmetric group. So yeah, so that's what we'll spend the rest of the talk discussing. So we'll see some examples in the Symmetric group, and we'll also see some examples in the perfect matching scheme. And so I think Ryan called the symplectic group the weird uncle of the Lie family. And so let's call this the weird uncle of the symmetric group family. Okay, so this is and in fact this group here is it actually is quite similar to the symplectic group in many ways, but I won't get into that. All right, cool. So the symmetric group scheme. So first, we need to discuss what the associates and the idempotents are. Right. And so these are indexed by half-eaten chocolate bars. Okay. So here's the chocolate bar that we associate to the integer partition 5331. Okay. And so the associate corresponding to this integer partition, it's just, this is, again, these are the Cayley graphs generated by the conjugacy class corresponding to lambda. These E lambdas, these are projectors onto the isotypic components of the regular representation of the symmetric group. So if you don't know what that is, that's fine. It's just, it's this vector space here where these S lambdas are the spec modules. And there's a nice tidy way of looking at the dimension of these spec modules, and they're these things that are in terms of standard Young tableau. Okay, so what's a standard Young tableau? Well, here's an example of one. Okay, so for this shape here, I put the numbers 1 through 12 in the chocolate bar, and I insist that my rows are strictly increasing, and going down columns, I'm also strictly increasing. Okay, so there's a lot of ways you can do that, and so the dimensions of these eigenspaces are really big. And this is actually useful in practice when you're doing things in extremal combinatorics. Won't get into that, but it's nice that they're big for some applications. Okay, and so this is the picture that I want us to be thinking about when we're doing, when we're thinking about functions on the symmetric group. So in the hypercube, we had this nice decomposition into Fourier levels, and we have the same thing for the symmetric group. So the way that we just talk about the levels here is that I look at the number of cells below the first row. So I round up all of these V lambdas such that V lambda has K cells under the first row, K or fewer, and that's the degree K functions. Okay, and over here, so we had the parity function for the hypercube. So we don't have the parity function, but we have the sign function, and it's essentially it's the analogous thing for the symmetric group. So there's this nice this nice parallel to what we're used to in the hypercube. All right. So here's an honest question. So if you're looking at this with fresh eyes,
was everything is not in the top row of the degree was the number of elements in that are not in the top row.
Right. Exactly. Yeah, so an honest question when you see these things for the first time, it's like, okay, well, let's start with the basics. Like, what can I say about the Boolean degree T functions? Okay, so the first thing you might think of is like, okay, maybe one of these T-umvirates or these Junta type families. So these are the ones where I pick T distinct coordinates for the left-hand side, T distinct coordinates for the right-hand side, and I insist that every member in my family maps IK to JK. Okay. So its characteristic function as a polynomial. So here our indeterminates are no longer just single variables, but pairs of variables. So we have matrix indeterminates. And it's just this, it's what you'd expect. So I plop in a permutation matrix. And if that, when I plop in the permutation matrix, if that's a 1, then that indicates that I'm in the T-umvirate. Okay, so I'm putting this in bold, but you might think oh, this is completely obvious, right? You just told me these are the polynomials that indicate my family. of course, they're going to be Fourier degree T functions. And so I would say it actually requires proof now. So we're not in Kansas anymore. Okay. So for the hypercube, yeah, I completely agree with you. But when you're doing Fourier analysis over other spaces, we have to do representation theory now to prove this fact, that the Fourier degree equals the polynomial degree. And it's not hard. I mean, if you've taken a first course in it, we have things like Frobenius reciprocity and induction. Those are the tools that you need to prove such things, but it still requires proof. And so, it seems like a trivial fact, but this is sort of what drives a lot of results in extremal combinatorics of the T-intersecting variety, which we'll talk about here momentarily. But this is, it seems trivial, but it's actually, this is what I think is a deep fact.
So polynomial degree here is just, I take a function, it's the smallest t such that I can write it as a linear combination of those.
Exactly.
And then the Fourier degree is the smallest k such that, yeah. We just said yeah, but
the maximum can you have a non-zero component in one of these.
Okay. Okay. So
it's not like just trivial from some kind, just find like because of the like just basically it's just finding a large enough invariant. Like just basically saying that they're both invariant under the same set of things. So I find if you say no, I'm not.
well, I think what you're saying is needs to be made more rigorous, and that's kind of what representation does for you. But if you can find an easier way to do it without representation theory, let me know.
I just meant when you conjugate those like Young tableau, then I'm basically, I mean, I'm just saying like there's no easy way to see this just in terms of sort of the set of operations that essentially preserve the space of monomials and also preserve the space of the Young tableau of the form set.
Yeah, but you still need to know like what space those monomials span. And so, and this was done years ago by Young, but it's.
You need to know how conjugation acts on the Young tableaus. So, okay, I was.
Yeah. We'll talk about it afterwards. Okay, so right. So we've talked about Juntas, and so now let's talk more about intersecting families. Okay, so what's the connection here between these T-umvirates and intersecting families? Well, okay, so first let's describe what it means to be T-intersecting for permutations. Okay, so I argue for sets, it's quite obvious, but maybe for permutations, it's not so much. But a family of permutations is going to be T-intersecting if any two members agree on T symbols. That means that they agree on where T symbols are mapped. So another way you can phrase this is that they're independent sets of this graph, GT, and where these associates are ranging over lambda such that lambda has less than T1s. Okay, so this is a regular graph, and the independent sets of this graph are the T-intersecting families. And this is just by definition, okay? So this graph, it lives in an association scheme, so that's going to be important. But that's an equivalent way of defining T-intersecting. So now these T-invirates, these are pretty big intersecting families, okay? They have size n minus T factorial. Okay, it's because I've fixed T coordinates and then I let the rest vary. They can be whatever you want. But is this the best that we can do? Okay, so we have a good lower bound on these T-intersecting families. Is this actually an upper bound as well? So Deza and Frankl, two famous extremal combinatorists, they seem to think so. And this was a conjecture from back in the 70s. And this conjecture has been very important in extremal combinatorics. It's like, the first paper by Ellis, Friedman, and Papel was, I think, one of the first, it was like one of the first time that we went beyond the cube in a non-trivial way, I think, in the extremal combinatorics. And it spawned a lot of creativity. There's been a saga of really impressive work that's followed it, where more ingenious ways of proving this theorem have been discovered. And as we get further to the right on the list, this function here becomes closer to the truth. Okay, still not solved in its entirety, but we have very good bounds on what n naught can be. But it's a very important theorem. And I'm going to talk a bit about the first proof, which uses the Hoffman bound. So I think we've seen the Hoffman bound maybe already in this workshop, but I'll remind us. So it's a bound on the independence number of a graph, alpha G, based on the largest and least eigenvalues. So I can find, so A is going to be any weighted adjacency matrix of G. And we can bound the size of the independence number in terms of the largest and least eigenvalues, okay? And so if equality holds, then we get a stronger condition, and namely that the characteristic vectors of these maximum independent sets, they all have to lie in the direct sum of the greatest and least eigenspaces. So this gives us additional structure, and this is going to be crucial for this, when we sketch the proof of this result by Ellis, Friedgood, and Papel. Okay, but I want to note before we sketch this proof that the best bounds are for this problem are known via hypercontractivity results on the symmetric group, and this is due to Nathan Keller, Noam Lifshitz, Dor Menzer, and Ohad Scheinfeld. Okay, and so hopefully we'll hear more about this result down here at the bottom as the workshop progresses. So it's very nice. Okay, but let's talk about let's go over a sketch of the Ellis, Friedgood, and Papel result. Okay, so recall that we had this graph. Okay, this graph is like encoding our problem of finding a maximum T intersecting family. I want to know I want to characterize the maximum independent sets of this graph. Okay, so as you know, this is a hopeless question in general, but this is a very structured graph, and so we have a chance of doing something. And so we want to find a weighted adjacency matrix A of GT. We're going to normalize this thing so that the maximum eigenvalue is 1. All right, and then we want to find we want equality to hold in the Hoffman bound, and so we want this to be true. We want this equality to be true. Okay, so we fixed everything else. We just solve for the minimum eigenvalue. Okay, call that zeta. Okay. So what's crucial here is that if equality does hold, then by this condition, the second condition of Hoffman's bound, then we know that these maximum independent sets, they have to lie in the span of the least and largest eigenspaces. But we know we already have an idea of what these should be. These should be the T umbrates that we just talked about. And remember, we said that the T umbrates, these were they spanned the Fourier levels from 0 to T. So we already had, so it's not, we're not just shooting in the dark here, trying to find a weighted adjacency matrix, right? If I tell you to find a weighted adjacency matrix, that's like more than enough rope to hang yourself with, right? So we need to know more if we're going to ever expect to find an A that meets this with equality. And so at least we know that what the eigenvalues should be for the levels 0 through T. Okay, and it turns out that this is actually going to be enough. And so rather than arbitrarily placing weights on the graph, we're gonna weight now our associates that compose GT. And so because these things come from an association scheme, when we find these weights, when we put weights on the associates, this has a completely predictable property on the eigenvalues. Okay, so it just they're simultaneously diagonalizable. And so this means that we can, when we place these weights, we can actually analyze what the spectrum of this weighted graph is going to be. And so we solve a linear system for X, but this isn't just any old linear system. You have to be very careful about which linear system you choose in order to find these weights X lambda. And this is where it's like knowing a thing or two about representation theory of the symmetric group is extremely helpful. And so this is in particular like asymptotic properties about about the representation theory of the symmetric group. The buzzword in math is representation stability. So these properties, it's useful to know them and then argue that after you solve this linear system, you get the x's. And then as when n is sufficiently large, then zeta is in fact the least eigenvalue. Okay, and so that's the gist of the proof. And I wanted to go over this proof because it's there's actually a lot of proofs in extremal combinatorics of t-intersecting results that proceed in this manner. Okay, so it's like, so if you get the gist of this proof, then you get the gist of a lot of these t-intersecting results. And another way of looking at this is that this Hoffman bound is actually an upper bound on the Lovász theta number. Okay, and then so the Lovász theta number is it's a relaxation of the it's a semi-definite relaxation of the independence number of a graph. And sandwiched in between is the Shannon capacity of a graph. So when you have equality holding in the Hoffman bound, you're actually showing something stronger. You're showing that you've characterized the Shannon capacity of the graph as well. And this is a very hard question in general. In fact, we don't even know if it's decidable. And so these spectral proofs, I want to argue that okay, maybe they're outclassed in some respects by the analytical methods that we know now, but technically it gives stronger results. All right, so maybe that's all I want to say about the t-intersecting families. So I want to consider a new problem now where the Hoffman bound fails spectacularly. Okay, so we're going to define this graph. We're still in the symmetric group association scheme. And this is the sum of the associates that are these hook-shaped partitions. Okay. So I have again a regular graph that's the sum of these hook associates, and I argue that this is actually the one skeleton of a very important polytope in combinatorial optimization, namely this thing called the Birkhoff Polytope, or equivalently the perfect matching polytope of K and N. Okay. And so, the way to see that is that two vertices are adjacent in the perfect matching polytope of K and N, or any graph for that matter. If when I take their difference, I get a single cycle. Okay, so that condition defines the edges of the Birkhoff polytope. So this actually came up quite naturally in Pain by Kane, Lovett, and Rao in 2017 when they were looking at a coding theory question where they wanted to bound the size of an alphabet in these class of codes called maximally recoverable. So, and I won't explain how they reduced it to this problem. It's quite clever, but their problem it amounted to determining what's the independence number of this graph. So if you compute the eigenvalues of this graph, it can be done. It's no picnic, but even if you do it, then naively, Hoffman only gives you n-1 factorial. And this seems far from the truth because these one skeletons of 0-1 polytopes, they shouldn't have independent sets that are that big. So this seems like a lie. And so what KLR did in 2017 was give a structure versus pseudorandomness argument. Okay. And it gives a substantially better bound, and that's what they needed for their result. And so the way it works, the way that the pseudorandom argument went is as follows. So if I take a set of the symmetric group, and if that's not pseudorandom or global, so I'm being a little bit vague here, but what this means essentially is that many members agree on the same, on some symbol set. Okay. And when you have many members agreeing on some symbol set, that means that you can get a density bump. So you just restrict to those families, to those members that agree on that T set and then recurse. Okay, easy enough. If that's not the case, then they use Fourier analysis on the symmetric group to show that there must be two permutations that differ by an n cycle. Okay, and the way that they did that was using this nice fact from representation theory that if you've been attending the representation theory reading group, you've seen this. And it's this fact that this associate here, so this guy up here, the single cycle, it has a very sparse Fourier support. So I can write it in the E basis as just n idempotents, not the number of partitions. Many, there's many lambdas, but it's only supported on the hooks. This is quite remarkable, and so this simplified their analysis greatly to where they could show that if I have some family that's pseudo-random, then I have to have some support on the n cycle. And if I have support on the n cycle, then I'm not independent. And so that's essentially the proof. And so I think Fernando's in the audience. With his co-author Carigliano, they were able to improve KLR by considering more than just the n cycle. So this argument is just the n cycle, right? But I have these other cycles. If you consider more of these other cycles, then you get better bounds. And so they conjecture that the proper bound should be 2n rather than 1.97. And I believe them. Okay, so open questions here that have been kind of discussed around the workshop. So what about the clique numbers of these graphs? So if you can, I argue this is another interesting question. And if you could solve this for like the non-bipartite analog, which I won't get into, you can look at the matching polytope of K2n. So then you can look at its one skeleton. And if you could tell me what the clique number of that graph is, then there would be some applications to structural graph theory. That would be nice, but seems like a hard question. Okay, so moving on to the perfect matching scheme. So this is the weird uncle that we're going to talk about now that nobody talks about, but me. That was, the weird uncle was the subject of my dissertation, so I know a lot about him. So first off, there's so if I take the odd numbers less than 2n and I multiply them all together, this is like the odd double factorial, and that's how many perfect matchings there are, because we can realize the perfect matchings as a quotient of the symmetric group. So they're cosets. We're modding out by this thing that's related to the symplectic group. It's called the hyperoctahedral group. Okay, so we have an analogous relation for our associates of this association scheme now. So it's more combinatorial. So, if you take the union of two perfect matchings, I get a disjoint union of even cycles. Divide each of those cycle lengths by 2, I get an integer partition of n. And so if that's your isomorphism type, when I union two perfect matchings together, I put a 1 there. Okay, and so these projectors, these are similar to the symmetric group, but now we're just projecting onto the spec module where this 2 lambda means that I'm doubling each part of lambda. Okay, so I won't get into it, but there's a parallel story to these T-intersecting results for the perfect matching scheme, and it's a similar journey that you take with Ellis, Friedman, and Poppel, but you need to sort of know more algebra, and you have to do things from scratch because there's less things that you can take off the shelf when you're studying perfect matchings, and so some of these you have to develop yourself, and so that's basically the gist of it. But what I really want to talk about is this thing called the matchings connectivity matrix, which this was really unexpected, by the way. Like I was reading some papers by Krach, Seigen, and Netterloff a while ago, where they were looking at parameterized algorithms for counting Hamiltonian cycles modulo 2. Sounds a little silly, perfect matchings. If I want to count perfect matchings modulo 2, I just compute a determinant. So, but when you do Hamiltonian cycles, it's still a hard problem. And so it's quite interesting actually. And so they were looking at parameterized algorithms, things parameterized by like tree width, path width, you name it width, and so they were, and this matrix came up, and so it was used as sort of in a data structure that they had. And what Jesper Netterloff found was that this matrix here, which is just the n associate of the perfect matching scheme, it had like incredibly low rank over GF2. And when you have incredibly low rank, then you can represent this matrix using far fewer than 2n minus 1 double factorial vectors. So it's And this led to some nice speed ups in so counting Hamiltonian cycles modulo 2, and even determining Hamiltonicity in some of these graph classes. So remember, so the less weird version of AN in the symmetric group, this had sparse Fourier support. So we said that it was supported on the hooks, and this is what led to that nice result by KLR. And so the question is, maybe a similar phenomenon happens here for the matchings connectivity matrix. And so it turns out that it does. So this is what Kurtikapian, I think, and Jesper Nederlov and myself showed. So here, it's not a sum over the hooks, but it's over a sum over these things that don't have this chocolate bar as a subshape. So if this were hooks, then it would just be the 2x2 chocolate bar. But this is the 3x2 chocolate bar. And so remember that this F2 lambda, we're counting standard Young tableau of shape 2 lambda. And so these are, so the rank of this thing is quite sparse. Compared this to 2n minus 1 double factorial. It's quite small. And this notation here, this is meaning we're like sweeping polynomials even under the rug. And but for parameterized complexity, for hard results, they're fine with that. So yeah, we don't care about polynomials. Just tell me the exponent. Okay, and so this result, I won't get into the details here. There's not much representation theory, if any, in how we conclude this. It's a difficult reduction, but once you have this bound on the rank, you can show that a lot of these known parameterized algorithms for parameterized DP algorithms for counting Hamiltonian cycles are optimal, assuming the strong exponential time hypothesis. So yeah, so this is a place where representation theory, I mean, it sort of naturally comes at you. You have this very symmetric matrix, and you want to know its rank, and so this is a very doable thing. So and in general, like anytime you're dealing with matrices that are invariant under some group action, you should be using representation theory. So this is all the examples that we've seen so far fall into this category. So that's if you pick up anything from this talk, just know that that's a good rule of thumb for using representation theory. Okay, and so I could not for the life of me figure out what the rank of this matrix was for primes other than 2. So that was already done by Jesper, but if you could do this, then you could get results, Seth hardness results for counting Hamiltonian cycles modulo P. So that would be quite interesting. So, and the representation theory way of tackling this would be like to look at modular representation theory. And that's much harder. That's much harder than what we've been discussing here. So we've been in the characteristic 0 case. And so it's quite difficult. All right, so what do we got here? We got about 5 minutes left, if I'm counting correctly. So I want to conclude with some new work that I've been doing with Yuval Filmus and co-authors. And this is, we'll call it New Beginnings of Boolean Functions, okay? So I deftly dodged a question that we asked many, many slides ago. And that was, can we classify the Boolean degree K or whatever functions? So I gave you one example of some, but I certainly didn't classify them. And this turns out to be a very difficult problem. Okay, so even for d equals 2, this seems like a hard problem. And even if we go to the Grassmann scheme, we still don't know yet what the answer is for d equals 1. And this is joint work, or this, I'm not part of this paper. This is Filmus and Ehringer. This was done somewhat recently. So for d equals 1, it's kind of what you'd expect. It's like these disjoint unions of dictators. Okay, so there's no surprises there. But even for d equals 2, we have no idea. And so this, the natural question here at this point is like, okay, well, if we can't classify things completely, then can we do this indirectly? And so the way we do this in the analysis of Boolean functions is via complexity measures. And so then the natural question is, these complexity measures on the Boolean cube, do they go beyond to the symmetric group and even further? And this was joint work with several co-authors. So all of these complexity measures appropriately defined, which I won't define them, but they can be defined appropriately, and they do generalize quite nicely. So they're all polynomially related. And so the place where representation theory rears its head up the most would be probably in this proof of the of sensitivity. So we use representation theory in a very clever way there to show an analog of the sensitivity conjecture for the symmetric group. But I won't get into that, into the details at least. And I want to conclude with some recent work with Yuval Filmus on harmonic polynomials on the symmetric group. Okay, so I think maybe by now we know that, okay, even like classifying Boolean degree D functions on these other domains, these other Earth-like planets, it seems hard. I won't say impossible, but it's hard. Let's go for an even easier question. So on the hypercube, this is like chapter 1 of O'Donnell's book. You know, everything admits a unique multilinear representation. So is this true when we travel beyond the cube? It's not true. Okay, so take the Johnson scheme. So I argue that if I plop in a K set here, that's always going to be 0 for trivial reasons. Even more trivial for the symmetric group. I can't have two edges adjacent to the same vertex. And this is like the the constraints in the bipartite matching polytope, right? So this always has to be true. Put the 1 over there, and it's the same constraints that you've seen before in combinatorial optimization. So there's lots of different ways you can write the 0 function, and this is sort of pump the brakes. We should figure this out before we try to go seriously beyond the cube. And so for the Johnson scheme, Dunkel found a way around this by giving a unique harmonic multilinear representation for functions on the slice. So what does this mean? Okay, so I have a function, and I take all the ways that I can write this function as a polynomial. Only one of those ways is going to be annihilated by a particular differential operator that Dunkel defines, and I won't get into the details of this, but there's a canonical way of writing things on the slice as a harmonic multilinear polynomial. And harmonic here just means that it's annihilated by some differential operator that we define. So the question is, okay, well, can we do this for the symmetric group? So can we generalize Dunkel's result to the symmetric group? And so we have about a minute left. And so I've defined, so all I'm going to say is yes, we can. And so if you want to, you can check out this somewhat new result that Yuval and I showed where we were able to do this on the symmetric group, but also more generally on perfect matchings. And so here, you can sort of think of the symmetric group and perfect matchings of K2N as being sort of very, very similar. They're both perfect. So Sn, this is just perfect matchings of K and N. Okay. And so there's a cool way of like proving results in algebraic combinatorics for Sn and perfect matchings of K2N simultaneously. So you don't have to like have 2 separate proofs necessarily. And these things are called Jack polynomials. And I won't get into the details there, but it's there's some really cool algebraic combinatorics that pops up when you start answering these sorts of questions about questions that we care about, moving to other Earth-like planets. And so it has connections to other areas of math. Okay, and so it's I think there's opportunity for cross-pollination here. So I think I'll leave it at that, but thanks for your time.
Questions?
So Dunkel's thing works for like in a more broader setup. So here do you have like, instead of Sn, if you have considered groups of like type B or type C or something, and you hope for a
so we haven't thought about that, but that's a good, I would imagine that what's that?
Probably works.
It probably works. Yeah. So I guess so for Bn, I definitely see how it would work, but maybe for Dn's the even weirder uncle, right? It's the uncle that nobody writes.
The new stuff.
or the other like perfect matching scheme, stuff like that, just by taking quotients of Sn and somehow lifting it to Sn, the problem is that.
So, yeah, it could be that these hypercontractivity and things like that, you can realize this on the symmetric group or on the perfect matching scheme by doing these quotients. I haven't worked out the details. What I'm really interested in for these T-intersecting results is like getting exact. I know that might be unpopular here, but like getting like what the, getting exact bound. So like for all n greater than 2t or something like that. What's that?
Like we have for sets.
Yeah, like we have for sets. So like this is some, if you've seen some of these, so the proof we gave, we punted into infinity to say that everything works out with these minimum eigenvalues. But if you look at a similar proof for the Johnson scheme, they don't punt. In fact, they go for it on fourth and goal, and they make it. So they do things exactly. And so that I'm thinking maybe some of this stuff that Yuval and I have been doing might have a chance of solving it exactly. That's very wishful thinking, but I haven't given up on it yet.
Okay, if there are no more questions, let's thank Megan again. Okay, and the workshop is done. So let's thank all of the speakers again.